Good day, everyone. My name is Chris Marine, and I am the Chief Operating Officer here at McObject. Thank you for joining us for our webinar, Is Hard Real-Time Possible with the DBMS? Hopefully you're somewhat familiar with who we are. Our experiences are deep in embedded development with database management systems, and we have customers with over 30 million copies of our products deployed in all types of applications around the world. That experience has put us in a position where we hear the term real-time used frequently, and we found that term to be greatly abused. Often, it is equated with really fast, which is important, but there's a lot more to it than that, especially with hard real-time systems. In this session, we'll explore how to achieve true real-time performance with a DBMS. First, McObject CEO Steve Graves will take you through our main presentation. After that, we'll have time for questions based on the presentation and about database technology in general. I'd like to introduce you to Steve Graves, our co-founder and CEO, who will be covering our topic today. Steve has been involved in embedded database architecture and engineering for over 30 years and brings a wealth of experience in solving real-world problems in the arena. Steve?
Okay, thanks, Chris. And as Chris just mentioned, back in 2001, we started McObject to bring to market the first in-memory embedded database written explicitly for embedded systems. In-memory databases were a bit of a novelty back in 2001, and before EXtremeDB, there simply wasn't one for embedded systems. If you needed one, you had to write it. Today, virtually every database vendor is expected to have support for in-memory databases. With EXtremeDB RT, it's deja vu all over again. We brought to market the first hard real-time deterministic database system for mission and safety critical real-time systems. So today we're going to explore what is and what isn't a real-time database system. Surprisingly, it isn't as straightforward as you might think. Consistency is an important topic for database system vendors. Real-time adds a new aspect that we're going to examine. And there are different algorithms for scheduling database transactions in real-time database systems. We'll take a look at two of those algorithms, highlight how they affect the execution of transactions and how to use that information to select the best algorithm for a system's execution pattern. A key tenet for real-time database systems is deadline management. Transactions must complete within preset deadlines, so we'll look at how that's implemented. And lastly, before we open it up for questions and answers, we'll explain why a real-time database system must, or at least should, operate in a real-time operating system. The terms mission critical and real-time are often used together, but they're actually orthogonal. For example, consider a medical device that administers therapeutic radiation. It is both real-time and mission critical. On the other hand, a system that handles financial transactions is mission critical, but it's not real-time. Were it to fail, the result could be financial losses. However, there isn't any time interval in which a transaction must complete, so it isn't real-time. And lastly, the control software that runs the print head on an inkjet printer is real-time, but is not mission critical. If the appropriate amount of ink is not deposited in time, you'd end up with a spoiled page that no one's going to end up dead. The vast majority of software is neither mission critical nor real-time. Don't fall into the trap of confusing fast and real-time. To be honest, embedded database system vendors have done a disservice in this regard, promoting their really fast, and I'm using air quotes here, really fast database systems as being suitable for real-time systems just because they're really fast. Sometimes with the caveat that the assertion only applies to so-called soft real-time systems. My company was guilty of this too. I resisted it for a long time, but insofar as virtually every competitor was making the claim, it essentially became a necessity. Since we released EXtremeDB RT, we've cleaned up the language on our website and other marketing materials so that when we talk about real-time, we mean real-time as in deterministic. Here's the thing. In real-time systems, there's a line in the sand with consequences. The line in the sand is the transaction deadline. Crossing that line means the transaction was late, so the real-time system was not able to respond to an event in the real world within the predefined timing constraint. In an advanced driving assistance system, for example, perhaps that means that an accident was not avoided. For non-real-time database vendors that rely on speed to stake their claim in real-time systems, speed is a figure of merit, nothing more. In fact, a real-time system isn't necessarily fast in whatever subjective way you want to measure speed. A real-time system is deterministic. And in contrast to real-time systems with high throughput systems, there isn't a separation between acceptable and unacceptable. A late answer is still a valid answer. Again, speed is meritorious, but it's not especially important for bragging rights, except for bragging rights, rather. So to belabor this point a bit more, in recent years, the term real-time has been abused by database vendors that have nothing to do with real-time systems. For example, Redis's homepage proclaims it to be the world's most loved real-time data platform. And Google claims that the Firebase real-time database is a cloud-hosted database, and well, that's just a built-in contradiction. What these vendors really mean is they support acting on live data. The database industry used to use the term active queries to mean query results or analytics that automatically updated as data streamed into the database. This is in contrast to having to poll the database, in other words, to having to re-execute a query to refresh the result set. To avoid confusion, the industry should get back to terms like active queries and live analytics, and as Chris mentioned, stop abusing the term real-time. So if those systems are not real-time, what is? Well, let's go back to the bullet from a previous slide. Real-time software is software that is considered to have failed if a timing deadline is not met. Ipso facto, a true real-time database system must enforce timing deadlines, which in this case means that transactions must complete, meaning they must either commit or abort within a deadline, but transactions can never be late. And you're going to hear me say that several times throughout the presentation. Transactions can never be late. So now it's necessary to define what a database transaction is. A database transaction is a logical unit of work that must be applied to the database in its entirety or not at all. In other words, it must be applied or not atomically. So a database transaction is not necessarily a single operation, although it may be. In other words, a sequence of operations, such as looking up one record, deleting 5 related records, and updating a field within the original record must all succeed or fail together. Likewise, a single update or delete command that affects 1 or 100 or 1,000 records must succeed for all or for none. Transactions are usually bound with explicit start and commit commands, or rollback or abort, as the case may be, that define the transaction block. Although in SQL database systems, each SQL statement can be treated as a standalone transaction. Most database systems adhere to what are called the ACID properties, where ACID is an acronym for atomicity, consistency, isolation, and durability. I just described atomicity. A transaction is applied in an atomic operation. Consistency means that applying a transaction to a database moves the database from one internally consistent state to a new internally consistent state. And when I say internally consistent, I mean everything within the database is consistent. The key structures are consistent with the data and vice versa. Isolation means that changes one transaction is making to the database cannot be seen by any other transaction until the first transaction commits that transaction. And lastly, durability means that once a transaction is confirmed as committed to the database, it's permanent. A real-time database must enforce an additional type of consistency. That being that the contents of the database are temporarily consistent with the real world, which we call external consistency, within some predefined time limit. So to summarize, non-real-time database systems usually enforce internal consistency. There are some exceptions though. There's 2 alternatives to ACID that are called BASE and the CAP theorem. BASE is an acronym for basically available, soft state, and the important part, eventually consistent. The CAP theorem stands for consistency, availability, and partition tolerance. And the theorem holds that in a system that implements the CAP theorem, you can have any 2 properties, but never all 3 properties. So with CAP, consistency may be the property that is sacrificed. BASE and CAP are intended to provide greater scalability than ACID. That assertion is pretty hotly debated in the database industry, but one thing is certain. BASE and CAP were born out of old school relational database systems' difficulty with scaling out. The current debate revolves around whether or not that's still the case. A real-time database system should, but is not required to enforce internal consistency just like any other ACID database, but it must also enforce external consistency. And performance is measured by the ratio of transactions that meet their deadline. In other words, they're successfully committed, to the number of transactions that miss their deadline. In other words, they were successfully aborted before the deadline. But in here, I'm going to repeat myself again, no transaction should ever be late. So developers of a real-time database system need to architect the system in such a way that it can guarantee that a transaction will never go past its deadline. To accomplish this, database system developers need to be able to inform real-time system developers when a transaction has to be aborted in order to meet the deadline. We did this by implementing a new transaction abort procedure that allows us to guarantee that the time required to reverse any modifications made within a transaction up to a point in time will not exceed the time required to apply those same modifications. Let me say that again. The time required to reverse any modifications made within a transaction up to a point in time will not exceed the time required to apply those same modifications. Now that, in turn, allows real-time system developers to use a pretty simplistic calculation to determine the point in time at which a transaction must commit or abort to meet the deadline, which is simply, as you see on the slide here, T2 divided by 2. There's a much more elaborate dissection of this that we don't have time to go into in today's presentation, but if you're interested, get a hold of me and I'll share it with you. So let's break down the timeline of a transaction. A transaction begins when the application invokes it. If the database system is busy with one or more other conflicting transactions, then the newly created transaction will be put into a waiting queue. But the clock on, the clock on its deadline has already started. It's conceivable that a transaction could time out without ever getting scheduled for execution. Of course, you want to avoid that, but it's a possibility. Once scheduled, the transaction begins executing, and we call this the workload interval. The database runtime cannot be a black hole from which emergence is indeterminate. What I mean is, when the system makes a call to the database runtime, the task cannot disappear inside the database runtime for an indeterminate amount of time, possibly exceeding the deadline before the database runtime returns control of the application. The database runtime needs to be aware of the deadline and be constantly looking at the clock and be able to return control to the application before it's too late to abort the transaction and allow it to finalize before the deadline. These are shown as deadline verification checkpoints on the slide. At some point, the transaction must commit or abort to allow the database runtime to finalize the transaction before the deadline. Therefore, a real-time database system must monitor the progress of the transaction and forcibly abort it when it can be determined that it's necessary in order for the transaction to complete before the deadline. This is the deadline control point on the slide. Remember, in a real-time database system, each transaction must complete before the deadline, and I'm going to repeat myself again, never be late. In a real-time database system, every transaction must complete before the deadline and never be late. And in this context, complete means meeting the deadline by successfully committing or successfully aborting. So the deadline is set by the application and passed as a parameter to the transaction start command. It's up to the system developers to assign that deadline. A rollback mechanism guarantees that the time to roll back a transaction is not greater than the time taken to apply the transaction up to a point in time, which allows a simple means of determining the transaction deadline. Again, it's simply 1/2 of the real world deadline, or T2 divided by 2 on the earlier slide. So in other words, let's say you have a real world deadline of 100 milliseconds. So T2 divided by 2 would be 50 milliseconds. So at the 50 millisecond mark, we need to either be committing that transaction or aborting that transaction to meet the real world deadline of 100 milliseconds. In reality, aborting a transaction can be substantially faster than the time taken to apply the transaction up to a point in time. So half the real world deadline is a worst case scenario that can be adjusted based on empirical data collected during testing and simulations. The transaction scheduling policy has an impact on the ratio of completed to aborted transactions. So let's explore two of these policies. The first will be high priority earliest deadline first, which I'll simply refer to as EDF. And the second is priority inheritance. With EDF, transactions are scheduled according to priority and within the same priority by the earliest deadline. Transaction priority is another parameter that gets passed to the database runtime through the transaction start command along with the deadline. And then with priority inheritance, transactions are scheduled, well, transactions that have the same priority are scheduled in, first out order without regard to their deadlines. So before we get into the differences between priority inheritance and EDF, let's summarize the mandate of the transaction scheduler. First and foremost, it must enforce the transaction deadline and then attempt to maximize the number of transactions that successfully commit their transactions relative to the number of tasks that have their transactions aborted. So the best way to evaluate the difference between EDF and priority inheritance schedulers is to examine use cases. This is an exercise that real-time system developers should go through in any case. So suppose we have three real-time tasks. HDB is a high priority task that wants to write to the database. M is a medium priority task that doesn't work with the database at all. And LDB is a low priority task that also wants to write to the database. So LDB starts the transaction first. After that, M comes in, and because it has a higher priority, it preempts LDB. But LDB still has exclusive access to the database because it's already started its transaction, even though it was preempted. So then next, HDB arrives, but is unable to start a transaction because LDB has the lock. In other words, it's going to go into the waiting queue. The highest priority thread, HDB, will have to wait until the lowest priority thread, LDB, completes its transaction, which in turn has to wait for M to yield to it. Consequently, by the time HDB gets the database, it doesn't have time to complete its transaction before the deadline. However, with priority inheritance, the operating system will be able to raise LDB's priority up to HDB's priority at the moment when HDB arrives, thus allowing LDB to preempt M and allowing LDB to complete its transaction and free the way for HDB, and both transactions will meet their deadlines. So in this scenario, priority inheritance is the superior transaction scheduler. So let me walk you through that here. Turn on annotations. Okay, so with the EDF transaction manager, LDB comes in first, and then M comes in, which preempts LDB. So LDB just has to wait for M to complete. Then LDB gets control again and completes. Meanwhile, HDB came in after M, but because LDB already had a transaction running, it went into the waiting queue until LDB finished its transaction. Then it got to run, but no longer had enough time to be able to meet its deadline. In contrast, with the priority inheritance transaction scheduler, LDB starts, M comes in and preempts it, and then HDB comes in with a higher priority, but because of the priority inheritance scheme, LDB's priority gets promoted to the same as HDB, so it gets to preempt M. So it continues running and finishes. And then HDB gets to run because it has higher priority than M. And it runs to completion before its deadline. And finally, when it's done, M gets to continue executing and meets its deadline. So in that scenario, the priority inheritance is the better transaction scheduler. Okay, let's look at the next one, the next example. Now we're going to look at a scenario in which EDF is superior. Again, we have three transactions, but all with the same priority this time. So this picture illustrates a scenario in which two transactions have arrived while a single transaction, the bottom one in the picture, is executing. In this scenario, the priority inheritance transaction manager would execute all three in an order that they are registered with the system. So again, remember, with priority inheritance, transactions that have the same priority are executed in first in, first out order without regard to their deadline. So it's possible that the deadline of the third transaction, the highest in the picture, and its deadline is shown as T1, is sooner than the deadline of the second transaction shown as T2. Consequently, the third transaction gets scheduled too late to complete before its deadline. But with EDF, because EDF schedules transactions in order of priority first and then within the same priority by deadline, the third transaction is going to get scheduled to run before the second transaction, even though it arrived in the queue after the second one, because its deadline is earlier than the second transaction's deadline. So as a result, with the EDF transaction scheduler, all three transactions are going to fit within their deadlines. So again, let me walk you through that. So with priority inheritance, things get executed in, first out order. So number one executes to completion, number two waits for number one, and then executes to completion. Number three waits for number one and number two, and then gets to run, but it no longer has enough time to meet its deadline. With EDF, because the transactions with the same priority are scheduled according to their deadline, number one comes in first. There's no conflict, so it runs immediately. Number two comes in next and gets put into the waiting queue. Number three comes in third, but it has a sooner deadline than number two, so it's the next one that gets to execute when number one finishes. So then it executes. And when number three completes, then finally number two gets to finish, and they all finish before their deadline. So in this scenario, where you got multiple tasks all running at the same priority, earliest deadline first is going to be the better transaction manager. Now, a real-time database system's efforts to schedule transactions such that the greatest number of transactions commit before their deadlines can be fruitless if the operating system doesn't provide appropriate support. That's why I said early on, real-time database system needs to run in the context of a real-time operating system. To illustrate this, we executed real-time database transactions on Mac OS and on a real-time operating system, one called DOS from DDCI. In the first test, with read-only database transactions of equal priority and the EDF scheduling policy, 12% of the transactions on Mac OS were aborted, whereas no transactions were aborted with DOS. So clearly, running with a real-time operating system was superior to running with a standard desktop operating system. And in the second test, with a higher priority task and a transaction writing to the database and a lower priority task that's reading from the database, 1.5% of the write transactions and 12% of the read-only transactions on Mac OS were aborted. Under the RTOS, only 0.08% of the write transactions and 13% of the read-only transactions were aborted. So roughly the same number of read transactions were aborted, but substantially less, an order of magnitude less of the write transactions got aborted with the real-time operating system. So again, it's pretty clear to see that a real-time operating system is really required to get optimal performance out of a real-time database system. And that's because an RTOS guarantees the CPU budget that's allotted to a task. With non-real-time operating systems, the time allotted to tasks is a suggestion, not a guarantee. So wrapping this up, I hope I've done an adequate job of explaining that the responsibility of a real-time database system encompasses that of a conventional database system's responsibility to maintain internal database consistency, but expands to include the responsibility to maintain consistency with the real world. I hope I've also highlighted that real-time doesn't mean real fast. The metrics used to measure real-time and non-real-time database systems not only are, but they have to be different. And we've learned that database transaction scheduling policies for real-time systems are not a one-size-fits-all proposition. You need to understand that the operational characteristics of the real-time system, you need to understand the operational characteristics of the real-time system and choose or implement a transaction scheduling policy that will maximize the number of successfully committed transactions versus those that are aborted to avoid missing their deadline. And lastly, we've just seen that an RTOS really is necessary to get the full benefit of a real-time database system. So with that, I'm going to pass it back over to Chris. We have a few minutes left to take questions and answers.
Thanks, Steve. I'd like to take questions from the audience. You can type and send questions from the Q&A box on the bottom of your screen there. And we'll wait for some of those to come in here. Okay, I got one already from Roy. Roy asked, if this is the first commercial DBMS, real-time DBMS, how have people been solving this up till now? Why can't I just use any database and terminate the transaction when I need to?
Yeah, so that kind of goes back to Chris and mine's earlier, in fact, almost the first point. Really fast is not the same as real time. The problem is that even though the database system is really fast, it doesn't guarantee, a non-real-time database system doesn't give you any guarantee. And I'll go back to another point that I made earlier. What you can't have is to make a function call into the database runtime and disappear inside the database runtime with no awareness of the deadline, and then reemerge from the database runtime when your deadline's already expired. And that can happen if the database system isn't written with real-time requirements in mind. In other words, within the database runtime, you always need to be taking a peek at the clock and see where you are with respect to the deadline. And non-real-time database systems don't do that. They go into the runtime, they do whatever work has been commanded by the application, and they return control back to the application. So before EXtremeDB RT, what did people do? Well, they wrote it themselves. Or perhaps in some cases, they tried to retrofit some existing non-real-time database system to work within the confines of transactions. Chris?
All right, thanks, Steve. Got another question here from Samir. And Samir asked, EXtremeDB RT appears to only support the pessimistic concurrency model for database locking. Are there plans to implement optimistic concurrency like MVCC?
Yes, so that is correct. The current version of EXtremeDB RT uses pessimistic locking approach, which for embedded and real-time systems is almost always satisfactory for an in-memory database. Things happen so fast in an in-memory database that it doesn't usually make a lot of sense to try to do complex lock arbitration or incur the overhead of MVCC. And there is quite a bit of overhead involved with MVCC to make shadow copies and clean up those shadow copies when the transaction commits, and so on and so forth. So with an in-memory database system, the time that it takes to start a transaction, make some updates to the database, and commit the transaction is typically measured in microseconds, which is far less time than it would take to do all the housekeeping involved with either complex lock arbitration or MVCC. That said, there are circumstances where MVCC would be advantageous. So the roadmap for EXtremeDB is twofold. The next version of EXtremeDB RT will support persistence, and the version after that will support the optimistic concurrency control.
Okay, great. Thanks, Steve. Got a question that's come in from Alexander. He asked, from a software developer perspective, how is the deadline for transaction set? Is it timer clocks or something else?
Yeah, it's a measure of time. Yeah, and the granularity of that time is up to you to determine. It could be microseconds, milliseconds, whatever. That's an application developer's decision to make.
Okay, great. Then Daniel asked the question, you have lots of legacy deeply embedded systems deployed. What's the current typical resource requirements for EXtremeDB, and how does that map to mainstream embedded targets such as Cortex-M7, Cortex-A class devices?
Okay, really good question. So the code size of EXtremeDB RT is about 150K. And there's going to be some variability with that depending on what compiler is being used, what compiler optimization switches are being turned on, what the target processor is. You mentioned M7 and A cores. but could very well be a PowerPC or ARM, even x86. So those things are going to affect the code size. The other aspect of the so-called footprint is how efficiently the database system uses the memory for the database. So let's say you have 10 megabytes of raw data that you need to get into the database. How much memory are you going to need to store that 10 megabytes of raw data in the database system? EXtremeDB was written for embedded systems, so we always knew that we had to run in resource-constrained devices. So we use that memory as efficiently as we possibly can, and there's a number of techniques that we employ to do that, which could turn this into a really long answer. But we'll follow up and send you links to another webinar that's recorded and available for you to view on that topic. The short answer is EXtremeDB can require as little as 15% overhead if you're really, really judicious about how many indexes you define and things like that. So for that 10 megabytes of data, we would need 11.5 megabytes of memory to store it in that case. A more realistic number is probably on the order of 30 to 50%. So in that case, we might need 13 to 15 megabytes of memory to store that 10 megabytes of raw data. The biggest influencer of that overhead is how many indexes you define in the database. And while we organize our databases or our indexes rather, as efficiently as we possibly can in memory, there's still structures that take space. So the more you define, the more overhead there's going to be.
Okay, great. Thanks, Steve. I got another question here from Roberto, and he asked, are high priority earliest deadline first and priority inheritance the only two possible scheduling algorithms?
Well, they're the only two that are currently implemented. There are other algorithms that we're considering that perhaps one might take into consideration the overall weight of transactions as opposed to a simple priority and deadline, and then try to maximize that weight of successfully committed transactions. And there's a lot of academic research on various scheduling algorithms for real-time database systems, and we're looking at those, and we'll implement them as the market demands, basically.
Okay, great, thanks. Got a follow-on question here from Alexander. He says, he asked, what RTOSs are currently supported? Is there Azure RTOS or AWS free RTOS on the list?
Yes, so the Azure RTOS is basically the old ThreadX, and that is supported, as well as DOS, which I used in one of the examples in the presentation, Emboss from Sager, free RTOS, Integrity, LinksOS, Nucleus from Siemens, VxWorks from Wind River, and there's others that are in the works right now, but the names escape me at the moment. But basically, EXtremeDB RT is going to be available for any real-time operating system on any 32-bit architecture. EXtremeDB RT is also always going to be delivered in source code form because of the tight integration with the real-time operating system. It's really just a necessity that you have the source code. So if you're running on an RTOS that we haven't yet built EXtremeDB for, you'll be able to build it yourself on that RTOS from the source code.
Okay, great, Steve, thanks. And we have a question here that's come in from Mike, and he's asking, will you be adding support for persistence someday?
Yeah, that's what the guys have been working on since we first launched the first version of EXtremeDB RT, which in its current incarnation is an in-memory database. So the next version of EXtremeDB RT will support persistence, which turned out to be more challenging than you might think, because file systems tend to have the same problem that that non-real-time database systems do. You make a call to the file system and you just disappear inside the file system, and at some point in time, it returns control back to you. But the file system isn't aware of deadlines. So the guys are working with that now, and so far they've been working with M-File from Sager and with Reliance from Tuxera, and one other operating system. Again, the name escapes me, but that's in the works, and it'll be available probably next quarter.
Okay, great. Thanks, Steve. Well, it looks like we've run out of questions at the moment. If you think of one you'd like to ask and have us answer, we'll respond to you by email. Just contact us at the email address given on the screen that you see there. Thank you for attending this webinar today. We hope you found the session helpful and that you've gained a good understanding of how important choosing the right database management solution can be for a successful real-time implementation. Thank you again, and good day.